All of the rest of the lecture videos this week are about support vector machines. That is the other quasi-linear model that we're looking at this week. But we're going to sneak up on it in several steps. For the time being, we're going to consider a very similar setup to the one that we just had with the perceptron. Once again, we're looking at a linearly separable problem, and we're looking to create a hyperplane, a linear decision boundary with a threshold at 0. As in the case of AdaBoost, we're going to be using the -1, 1 notation for our negative and positive classes rather than 0 and 1 as we've used in a number of other cases. But these two are pretty much interchangeable anyway. The other difference is that we're going to explicitly separate out our intercept term as a separate scalar component rather than wrapping it in as a dummy feature into the weights vector at weight 0. So our model, our decision function, will look like this. So we've said that our data is linearly separable. What we want to do is to find a hyperplane that separates the two classes. Given that there is this separability, there must be an infinite number of such hyperplanes occupying the gap between the classes. So which of those would we like to use? To an algorithm like the perceptron, any boundary at all will do. If it finds one, it stops. That's it. But we might like to consider some other criteria. For example, let's have a look at this data. Just intuitively, do we think that this is a good boundary, or this, or perhaps this? Intuitively, all of those boundaries seem in some way suboptimal. And the reason for that really is that they are too close to the samples in one of the classes. Defining a boundary like that is really putting an awful lot of faith in the accuracy and stability and completeness of our training data. If there were small amounts of fluctuations arising from natural variation or measurement noise, then that could easily nudge a sample over that boundary and into the wrong classification. If we are interpreting the outputs of our linear model as a scoring function, then for points that are far away from the boundary, we have high confidence. Those that are very close to the boundary, we are really not very sure. What we would like to be able to do is make predictions that are as confident as possible and also as robust as we can make them. We might phrase that as a preference for boundaries that are as far away from the training samples as possible, while obviously still correctly separating the classes. So this boundary looks a lot more plausible. In this case, the distance away from the boundary of the nearest samples on each side has been chosen to be as big as it can be. Obviously, one consequence of that is that the distance on both sides of the boundary has to be the same. Let's call it the margin M, because if that wasn't the case, it would be possible to move the boundary towards the one which was longer and thereby get a bigger minimum. So what we're suggesting is a criterion for choosing the boundary that it should maximize the margin. We've previously defined the margin like this. This formulation is sometimes known as the functional margin. The arrows on the figure show what is known as the geometric margin, that is, the actual distance. The two are the same provided that W is a unit vector. You can always make the functional margin bigger just by scaling the weight vector by some large positive constant. Consequently, the functional margin is unbounded, and optimizing that, there's no maximum. So how do we fit a problem like this? Well, we can express it as a maximization problem on the geometric margin like this. There's some margin M. We want to choose W and B in order to maximize that, subject to two constraints. One of those constraints is that the W is a unit vector. That's to stop the problem being unbounded. The other constraint is that all of the points in the training set must have a margin greater than this thing we're trying to maximize. Now, this form of maximization is a little bit different from any that we've seen before because it contains constraints. Adding constraints to a problem changes what it is that you're maximizing. It's possible that some constraints may turn out not to matter. It may be that the optimum still stays in the same place. Conversely, they can change the whole problem completely. Let's just look at a simple example using a one-dimensional optimization of a quadratic loss. So this blue curve is representing our loss function that we want to minimize. So in the absence of constraints, the optimum is just at the bottom of the parabola here. If we add a linear constraint to the problem, in this case we're going to call it an equality constraint, then what we're looking for is points where the parabola intersects the line. There are two of these points, but obviously one is bigger than the other, and so the minimum is down here. If we consider the case of an inequality constraint, well, let's say that everything has to be below this line, then the constraint doesn't have an effect. The minimum of the loss is already below the line, and so the same minimum applies. But what if our inequality is that the solution must be greater than or equal to this constraining line? In that case, the true minimum of the loss function is not one of the available options, and the minimum given the constraint is at this intersection point here, the same as for the equality constraint. The classical approach to these kind of constrained optimization problems is to introduce what are known as Lagrange multipliers, which wrap the constraints into the objective function to create a new objective, and then solve that for its stationary points. There may be many of those, and then you have to choose between them. This approach extends to inequality constraints via the Karush-Kuhn-Tucker method. One notable condition for inequality constraints, as we've already seen in our trivial quadratic example, is that inequality constraints only ever actually matter if they are actually equality constraints. So they only become active at equality. This will be important in a few minutes. There are a number of special cases of constrained convex optimization problems for which there are efficient and stable solvers readily available pretty much off the shelf. We've briefly mentioned a couple of these in the past. There are linear programming problems, that is where you've got a linear objective and also linear constraints. This turns out to be equivalent to finding the minimum vertex of a simplex created by all the intersecting hyperplanes defining the constraints. Linear programming, or LP solvers, are readily available. There is this functionality is available directly in SciPy in the Optimize package. Another standard class of constrained convex optimization is quadratic programming. This is when the objective that you're trying to maximize is a quadratic function and you have one or more linear constraints applied to it. The simple example diagrammed earlier would qualify as a QP problem. Again, QP solvers are reasonably widely available, and we will eventually be using them to solve some of these problems. I also mentioned in a kind of throwaway way a couple of weeks ago that quadratic programming solvers are often used to solve the lasso regression problem. I'm not going to go into any details about how any of these things work, but if you're interested, the book on convex optimization by Boyd and Vandenberger is linked in the resources section of Moodle. For our purposes, we're just going to assume that it works. If we go back to our margin maximization problem, unfortunately, this is not one of those solvable classes. However, we can do a bit of juggling to make it into one. Firstly, the constraint that W must be a unit vector, we can merge into the other constraint by dividing through. That means that you can scale W however you like without increasing the margin. We can then take this W over to the right-hand side and have the equivalent constraint like this. So this constraint has to hold for any magnitude of W. We can arbitrarily choose to enforce that W has this magnitude. That is to say, it is exactly the reciprocal of whatever the margin is. This also incidentally scales B, but we don't need to care about that. It'll all come out in the wash. Doing this, we can eliminate M entirely from the maximization and make it solely a maximization in terms of W. But this norm of W is guaranteed to be positive, so if we're maximizing this, then we might as well minimize its reciprocal. And as in previous cases, we can apply scaling values or monotonic transformations. So if we're going to minimize this, we might as well minimize this. This is obviously a pretty blatant bit of choosing something for convenience because we know that we're going to differentiate it. So this optimization has a quadratic objective, it has linear constraints, therefore it is a quadratic programming problem. We could just rephrase it in the appropriate way and throw it into our QP solver and we'd be done. We're not going to do that. We're going to go a few steps forward in the optimization, and the reason we're going to do that is because it's going to reveal some interesting features of the solution to our problem. So the first step is to combine the constraints into the objective using Lagrange multipliers. There are a whole bunch of these. The multipliers are called alpha I. There's one for each of the training samples because we want to impose the margin constraint on all of those samples. This formulation is known as a Lagrangian, and it's specifically the primal objective of our optimization problem. We want to find its stationary points, so we differentiate it with respect to the things we're optimizing over, which is the W and B. We first differentiate with respect to W. So the first term, the half magnitude squared of W, the derivative of that, you may recall from a couple of weeks ago, is just W. This should also be pretty easy to spot just by thinking about the dependence on each of the terms. The derivative of the second part of the primal objective looks like this. The factor in front of the weights for each of the things in the sum is this alpha I, yi, xi. Again, xi dotted with w is just a linear form. We can set this expression to 0 and rearrange it. We get this formulation here. We see that w is just a weighted sum of the xi. This is interesting. We'll come back to it. We also need to differentiate with respect to the bias b. Bias is just a scalar, so this is just a scalar partial derivative, not a full vector gradient. The bias doesn't crop up in the first term of the objective at all, so the derivative is just that of the sum involving the alpha I, and it looks like this. Again, we set it to 0 and rearrange, and we find this. The sum of all the true labels multiplied by the alpha i's is just 0. Again, this is going to be useful. Remember it. We can substitute these conditions back into the primal objective. For the first term, we replace the w with the sum, and we expand the magnitude calculation as a dot product of two w's. Taking the second sum term piece by piece, The first part of it, the part involving yi, xi and w, we can expand again like this. It's another dot product because the w is the sum of alpha I, yi, xi, and so it expands like this. For the third term, the term involving the b, we get this. And finally, the minus 1 at the end just gives us this sum of the alpha i's. We're going to rearrange this. Let's just take that last term. That's going to stay as it is. That sum of the alpha I, yi, we've established already is 0, so that term will just disappear. Finally, this first big difference of dot products of sums at the beginning, well, the first term is just a half of all that stuff, and the second term is the whole one of all that stuff. A half minus 1 is just minus a half, so this comes through as minus a half times all of that. If we think about what's happening in that dot product, it's the terms in one sum being multiplied by the terms in the other sum. So we can combine all these together into a single double sum that looks like this. This is known as the dual objective. You'll note that we've removed the original variables from the objective altogether, and the dual is now expressed solely in terms of the alpha I. W and B don't appear at all. Note that this still isn't the solution, this is just conditions on solutions, and we still need to optimize in order to get the correct one. But for the dual problem, where the primal was a minimization, the dual problem is a maximization. We seek the values of alpha I that will maximize this expression. After all this, we still have a quadratic programming problem to solve in order to get the alpha i's, and then we want to use those to calculate our w and b, which are the things that we're really interested in. So you might wonder what the point was at all. But as I mentioned, when we do this, we discover some interesting features about the solution. So if we look back at the elements of the solution, we will discover some useful properties. The first of these is that thing we noted earlier, which is that the correct optimal w is a weighted sum of the input vectors. This is an example of something known as the representer theorem. The second really interesting and important property that we see here in the solution is that the fitting process, this dual optimization objective that we are going to solve, only depends on the input data in the form of pairwise inner products between individual vectors. It turns out that if we also substitute our weighted sum expression into the prediction function, then we get this, and again the prediction only depends on the data in the form of pairwise inner products. This will turn out to be very useful in a bit. The final important property is a little bit less obvious from the steps that we went through before, but it comes about as one of the Karush-Kuhn-Tucker conditions on the solution, which look like this. For all samples, the product of the coefficient alpha I and this margin constraint yi xi dot w plus b minus 1 must be 0. That means that if the margin constraint isn't 0, the corresponding coefficient has to be. This is another way of saying what we observed earlier in the simple quadratic optimization example, that inequality constraints only matter at equality. What that means is that only the samples that are actually on the margin contribute to the solution at all. For all the others, the ones that are beyond the margin, the alpha i's will be 0. So the solution depends only on a handful of the training samples. And these samples are known as support vectors.